Hi, in this lecture we look at implicit partial differentiation as well as the applications of partial differentiation. So suppose that an equation of the form if capital letter F of xy is equal to 0 defined y implicitly as a function of x. So this means that we have a function f of x y where y is an implicit function of x, right, in the domain of f. So we say that if small letter f is differentiable, then we can apply. So what does this mean? If it says that it is defined implicitly as a function of x in the domain of f, it means that y is equal to f of x where f capital letter x of f of x is equal to 0 for all x in the domain of f. So why am I writing it like this? We're saying that y is an implicit function of f, so we say that y is equal to f of x. And then here we had capital letter f of xy, but we know that y is equal to f of x, hence why we have that equation there. Okay. So we say that if f is differentiable, we apply chain rule to differentiate both sides of this equation with respect to x. And we take note that both x and y are functions of x. Okay, so what does it mean? How do we find then the derivative of y with respect to x? So let's do the following. So what we have capital letter f. We know that it is a function of x and it is a function of y. But we are told that x is a function of x and y is also a function of x that has been implicitly defined. So what does it mean then to take this derivative and set it equal to 0? By chain rule, we have that then this is partial f over partial x times dx over dx plus partial f over partial y times dy times dx equal to 0. So while dx means that you differentiate x with respect to x, which means it's 1. So you're left with df over dx plus. Now you have partial f over partial y times dy dx. This is equal to 0. So we are trying to solve for dy over dx. So then this means that dy over dx is going to be equal to minus partial f over partial x divided by partial f over partial y. Well, this is the same as, well, we have the minus, right? And f subscript x to denote the partial derivative of f with respect to x divided by the partial derivative of capital letter f with respect to y. So let us do an example where we apply the implicit function theorem, right? So let us recall the following. We did this previously, this example previously when we did implicit differentiation. So the way in which we did this function was to say, okay, so we're trying to find y prime. And x cubed plus y cubed is equal to 6xy. So this is an implicit function problem, right? So the way that we did it before was to differentiate both sides with respect to x, okay, which is equal to d dx times 6xy. So we remember that this was 3x squared plus 3y squared times dy dx is equal to, and on this side we apply product rule, which gave 6y plus 6x times dy dx, right? Then what we did was to put the terms that required or that had dy dx on one side and the other terms that did not have it on the other side. So then dy dx then becomes 6y minus 3x squared over 3y squared minus 6x. That is what we did before. But now, what we do is the following. We write, let capital letter f of xy be equal to, okay? So this one says the following. Instead of doing what we just did now, we let this function become a function of two variables, x and y. So it's up to you if you will say it is going to be equal to x cubed plus y cubed minus 6xy, or you will say it's 6xy minus x cubed minus y cubed, okay? Then, according to the result that we have just derived here, remember that you need to write it down, the whole formula. So you will say dy dx is equal to minus f subscript x over f subscript y, which means that it is minus. Now let us differentiate this function that we have just made a function of two variables with respect to x. Well, the derivative of x cubed is 3x squared with respect to x, and then when you differentiate y with respect to x partially, it's 0, and then 6y is considered as a constant, and then we differentiate x, we get 1, so then this is equal to minus 6y divided by, and then you do the denominator, which says you must now differentiate the function given here with respect to y, and then you get that it is actually equal to 3y squared minus 6x. So if you distribute the bracket there at the top, you get 6y minus 3x squared divided by 3y squared minus 6x. Okay, so basically we love the second part because it just says make this one a function of two variables and then use a formula and partial derivatives. We are done. We found the problem. Instead of what we were doing before, where we tried to make sure that dy dx is on one side. Okay, let's see another one. If e to the xy plus x plus y is equal to 1, evaluate dy dx. Okay, so once again, we need to make it a function of two variables. So we let capital letter f of xy. I think here it would be simpler to bring one on the other side. Doesn't matter, you'll get the same answer at the end of the day. That it is equal to e to the xy plus x plus y minus 1. So this is a function of two variables, and from the implicit function theorem, dx dy is equal to minus capital letter f subscript x over capital letter f subscript y. Okay, so let us differentiate then with respect to the x, which is what is happening in the numerator. So then if we differentiate a function exy, remember that I always say you treat it as, because we want to differentiate with respect to x, we will make it as something like e7x, and if you differentiate this is equal to e to the 7x times the derivative of the function that is happening in the exponent, so that is 7. But in this case we do not have a 7, we have a y. Okay, so that means that what we have here will be y e to the xy, right, plus then with respect to x it's something with a 1 because the other two are 0. Okay, then you divide this by, and then you differentiate at the numerator, the denominator, then you will get x e to the xy plus 1. Okay, right, now suppose that z is given implicitly as a function of x and y by an equation of the form capital letter f of xyz is equal to 0. So this means that f of xy is now instead of having a z there, we will substitute it as f of xy for all x in the domain of f. So if if capital letter F and small letter f are differentiable, then we can use chain rule to differentiate, and the equation f of x, y, z equal to 0, and we obtain the following. Okay, so this one, because it is no longer a function of nice two variables where one is implicitly defined as the other, because here we had something like this, f of x, y, but we knew that y is implicitly defined as a function of x. So it's like we were just dealing with a function of x on its own, hence why it was easy, or rather that's why it made sense for us to find dy dx. Okay, here we have that it is a function of three variables, of which the last variable z is an implicitly defined function of x and y. So that's why we will be required to find the partial derivative of x, and then the partial derivative of z with respect to x, as well as the partial derivative of z with respect to y. Because look at what we have ended up with. It is now a function of x and y. Okay, so that's why we then have the following formula. Okay, so before we had that dy dx is equal to minus, right? It was equal to minus f of x divided by f of y. Now, if you have to find the partial derivative, it is minus f of x over f of z. So do look at it like this. What happens in the numerator, the derivative of, is what we divide with when we make our function a function of two variables or three variables. And also, it is what happens here. What we say, we take the derivative with respect to x, then we differentiate that one, with respect to x, and so forth. Here we have that it is with y, so we have y there, and this is partial z, so we have fz at the denominator. So just if you practice more of these problems, you will actually end up seeing a certain pattern, right? So given that z is equal to e to the x sine y plus z, so once again you can go about solving this using implicit differentiation, the normal one that we did at the beginning, so lecture 1 of the section. Okay, we did do something like this. Okay, which in this case maybe we can do it. It is as follows. We would have to take the partial derivative with respect to x on both sides of z, and it is with respect to x as well as the numerator, as well as the right hand side. Okay, then we know that we are going to apply implicit differentiation. Z is a function that is implicitly defined with respect to x and y. Okay, so that means that we will have that z is equal to 1 times a partial z over partial x, because z is implicitly defined. Then the next thing here, we are going to apply product rule. Then I'm first going to differentiate the first function, which is e to the x. The derivative of e to the x is e to the x times, and then the second function, sine of y plus z. Plus, you keep the first function and you differentiate the second function. The derivative of sine of y plus z, we first differentiate the outer function, which is cos of y plus z, times the derivative of the inner function with respect to x. The derivative of y with respect to x, the partial derivative of y with respect to x is 0. And then the partial derivative of z with respect to x is 1, okay, times the partial derivative of z with respect to x. Reason being, z is implicitly defined, okay. Then we once again bring everything that has partial z partial x. So that means that we have 1 times partial z partial x minus e to the x cos y plus x times partial z partial x. This is equal to e to the x sine y plus z. Then you take out partial z partial x as a common factor, and you're left with 1 minus e to the x cos of y plus z equal to e to the x sine of y plus z. So then the partial derivative of z with respect to x is equal to e to the x sine y plus z over 1 minus e to the x cos of y plus z. This is what implicit differentiation said. However, remember that we use what now? We use the implicit function theorem. Okay. What we are using is called implicit function theorem. Remember that we are given that z is equal to e to the x sine of x plus y. Okay. So we are trying to find partial z partial x, and based on the implicit function theorem, it says that we need to compose a function of 3 variables. Okay, and then partial z partial x will be minus f subscript x divided by f subscript z. Okay, so let's see, how do we go about it? So we let z be equal to, or rather, we let f of x, y, z. So it is not a function of 2 variables, but a function of of 3 variables. So in this case, we were given that it is z is equal to this. So I'll bring everything to the other side. So I'll have z minus e to the x sine of y plus z. Now we will find, okay, so we now find partial z partial x using the theorem. And how does that one work? It says partial z partial x is equal to minus f this f z. Okay, so then let us then differentiate with respect to x. Remember what happens if you differentiate partially with respect to x? It means everything else is treated as a constant. Okay, so we differentiate z with respect to x. We no longer look at it as the fact that it is implicitly defined. We just consider anything other than x a constant. So basically here it is the same as differentiating minus e to the x sine of y plus z. But sine of y plus z is once again treated as a constant. And then you differentiate minus e to the x, it gives minus e to the x sine of y plus z. Divided by, now we have to differentiate with respect to z, this function here. So the derivative of z with respect to z is 1 minus e to the x sine, those things are considered as constants. E to the x is considered as a constant, and basically it's like we are trying to differentiate with respect to z sine of y plus z. And what does the chain rule say? The chain rule says it is you differentiating the outer function times the derivative of the inner function with respect to z, which is 1. So if we clean this up, we have a minus and a minus at the top, so it's e to the x sine of y plus z divided by 1 minus e to the x cos of y plus z. So that is how you do it, using the theorem. Now, right, the next one. We need to find partial z partial x and partial z partial y if we are given this function. I'm going to do partial z partial y now, and then I'll let you do partial z partial x for homework. So the first step is to let the function be a function of 3 variables, x, y, z. So this is equal to x cubed plus y cubed plus z cubed plus 6xyz minus 1. Or you can have it as 1 minus everything else that is happening there. Okay, so that's what we have, right? So now, in order to find partial z partial y, the formula says it is minus fy over fz. So we need to find the partial derivative with respect to y and divide it by the partial derivative with respect to x. So let's see. X cubed is 0, the derivative, and then y cubed, the derivative will be 3y squared. Okay? And then we have, if we continue, then we have plus z cubed is considered as a constant, and then the next one, we consider 6xz as a constant, and we differentiate with respect to y, so that is 6xz. Okay, and then we divide by the partial derivative with respect to z. That one gives 3z squared plus, then once again we consider this as a constant and you differentiate with respect to z, that function there, and then the derivative of z with respect to z is 1, so you have 6xy. So this can be written as minus here, and then this is 3y squared plus 6xz divided by 3z squared plus 6xy. I mean, if you were to divide everything by 3, then this is y negative y squared plus 2xz divided by z squared plus 2xy. So if you do it for partial z partial x, you should end up with minus x squared plus 2yz divided by z squared plus 2xy. Okay, now let us then look at the application to partial derivatives, and we will look at it. The application will be to partial differential equations known as PDEs, right? Then the following is going to happen. We are supposed to determine whether each of the following satisfies Laplace's equation. Laplace's equation says the second partial derivative with respect to x plus the second partial derivative with respect to y, so then that is order 2, is equal to 0. So this is how I usually prefer to do it. Right. Instead of trying to satisfy the equation, let's do this. We see that the equation requires uxx and uyy. So we first do ux, right, which is the partial derivative of u with respect to x. Small letter, remember, right? Small letter. So this is how it works. So if you differentiate it with respect to x, it means everything else is considered as a constant. So then you have that the derivative of sine x is cos x, and then you leave cos y, and then you have the derivative with respect to the derivative of cos x with respect to x, that is minus sine x sine hyperbolic y, right? And then now you find the second order derivative, okay, with respect to x. Remember, the second order says you differentiate what you just differentiated. In this case, partially with respect to x, right? What does it say? So now, once again, we differentiate, and everything else, since it's with respect to x, everything else is considered as a constant. So the derivative of cos x is minus sine x, and then cos y is considered as a constant, minus the derivative of sine x is cos x, and then the derivative of sine hyperbolic, this is something with respect to y, so it's a constant. Right, then now we need to go about the second part, uyy. So we first need uy. So this time around, it means everything that is with x here is considered as a constant. So that means sine x is left as it is. And then we find the derivative of cos y, which is sinh y, right, plus cos x, and then the derivative of sine hyperbolic y is cos y. Then you do the second derivative, So you get, once again, you leave sine x as it is, and then you differentiate sine hyperbolic y, which gives cos y, plus you have cos x, and then the derivative of cos y is sinh y. Right. So now remember, what is it that we are trying to do? We want to determine whether it satisfies the Laplace equation. In other words, if we take uxx plus uyy, will it be equal to 0? If it is equal to 0, then it satisfies the equation. Right. So let's see. So this is equal to, now we put uxx. Uxx is minus sine x cos y minus cos x sinh y, plus uyy, which is sine x cos y plus cos x sinh y. Well, we see that minus sine x cos y plus sine x cos y, that it is 0, minus cos x sine hyperbolic y plus cos x sine hyperbolic y, it's another 0, so this is equal to 0. So indeed, uxx plus uyy is equal to 0, so therefore, yes, it satisfies the Laplace equation. And then another one is this, okay? So I will give you the partial derivative with respect to xx, which is ex sine y minus ey cos x, and I'll give you uyy. Remember that you cannot get to uxx or uyy without first differentiating with respect to y partially and differentiating with respect to y partially. Okay, and then uyy is minus ex sine y plus ey cos x. You can see that if you add these two, that they will give you a 0. So you need to fill in the steps. So therefore, yes, it also satisfies the Laplace equation. Okay, thank you.